Hey guys, so today we're going to estimate price elasticity of demand in a way that we can actually check. We'll fit a few Bayesian models using PyMC, interpret whether they recover the economic story we care about, price, pooling across products, eventually even substitution between products. Um, yeah, if you're watching this, you probably already know what's price elasticity, but if you don't, we are also going to cover that real quick as well. So elasticity is just if I change price by 1%, what happens to quantity in percent terms? That's it. If I raise my price of 10%, what's the effect that has on demand? So price elasticity is usually negative. If you raise price, you sell less. But you also have some other effects like cross price elasticity. So that's about other products. If my competitors raise their prices, does my demand go up? That's substitution. And that could even be among my own products, like think Coca-Cola versus orange juice or chips versus chocolate, things like that. So yeah, why is that useful? If you have the model of quantity in terms of price, you can find optimal prices. You can see, okay, so what's the price level that will optimize my revenue or my profit? And it also helps to understand, what products are sensitive to price changes or not. That's it. So let's go through a notebook that I built for this using PyMC. Now, we're not going to cover the whole notebook because there's a lot of code here for synthetic data generation, plot creation, and all of that. But I will share a link to a GitHub repo where you can find the whole notebook. This is our data generating process. So basically, we are looking at logs here. So log of quantity is a function of log of price. Why do we do that? Very good question. There's a few ways to look at quantity in terms of price. So if you're looking at just levels, it's quantity equals like something times price. Log level, you could use level log, so you could apply log to either price and quantity. We're using the log model, which applies log to both quantity and price. That's good because the coefficient that you get, the beta, that will be, you can interpret that as a real elasticity coefficient. So a coefficient of, let's say, minus 1.5 means that 1% price increase will lead to 1.5% demand decrease directly. It also guarantees that demand stays positive. You shouldn't have negative quantities, and it just captures this like natural diminishing sensitive. Then it just makes sense from an economic point of view. And why using Bayesian models? Because you could just do like simple linear regression, the classic ordinary least squares. Bayesian methods give you good uncertainty quantification. You can use hierarchical models to share information between SKUs. So, if you have a category, you can use data from that category, and you can apply priors into Bayesian models. So yeah, that's it. The idea is to create a few product categories. In here, I have 3 in my synthetic data: essentials, beverages, and snacks. Why is that? These different categories, they have essentially different price elasticities. So here I'm making the distinction between on-price elasticity and cross-price elasticity. So on-price is like how much does the price change, let's say, in baby formula affect the demand for baby formula. And cross-price elasticity is, for instance, how much does the change of price in diapers affect baby formula or something like that. So we have these 3 different categories because essentials, they tend to have low elasticity. Basically, you need to buy them no matter what, so they're not very sensitive to price changes. Beverages, they are like more or less elastical. And then you have snacks, which are basically non-essential. So if they get too expensive, you just won't buy them. And cross-price elasticity here just means, baby formula and diapers, for example, the price of one of them does not affect the other one that much. In beverages, you can see more of that as well as in snacks. So I've created this synthetic data I've also created different elasticities for different regions. So basically, I just made Europe slightly more sensitive to price changes than America. And that's it. We're not going to waste too much time on the synthetic data creation. Um, so once we have that synthetic data set, this is what it looks like more or less. I've also added a couple different control variables here just to make things a little bit more interesting. You have a skew, you have its category, you have region, you have price, quantity, you have week. So basically it's like over time, price increased by this much, what happened to quantity. You also have log of price and log of quantity because that's what we're going to be using. And finally, you have the control variables that we are using. We just take a look at like how these behave. And yeah, essentially you can see that log of price has an impact on quantity, but that is different depending on the category. So, with diapers, you can increase price, but quantity won't change that much. Whereas let's say, with cookies, when price increases, then quantity rapidly decreases. Yeah, so first model we're going to build using PyMC. How does it work? Each product will get its own elasticity coefficient, of course, but they don't share information. We do not look yet at categories, things like that, cross-price effects. We just want to have a sort of baseline model. How do we build it? We have an alpha, which is essentially our intercept or a fixed term, let's say. We have to split elasticity into these two components just so that we get the right names at the end. But in practice, you could say, elasticity is minus, because here I have the sign of minus, and I'm using log normal here, distribution, to keep things positive, basically, with like normal distribution. You could get negative and positive values. And here I want to keep it strictly positive, so that when I use the minus sign, I get elasticity strictly negative. Yeah. Then I have, beta and sigma. So beta will be for each of the controls. I'm using normal because it's like very uninformative. I'm not sure how it looks like, so I'll just keep sort of like neutral. And then my final model is basically the alpha for that skew plus its elasticity coefficient times the log price plus the coefficient for season times seasonality plus the coefficient for economic index, which is another control, times that value. And then we'll take a sample using two chains. Yeah, we run that using PyMC. And then here, that's what I meant essentially, so that we can have the elasticity skew name here. But otherwise, it's just you have a log normal distribution for the elasticity, and that's it. You have your alpha, and then each of these variables is contributing to the observed values, which are the quantities. We have a quick model diagnostic here. Essentially, what we want here on the right is to see that the values don't have a clear trend. They look, we call it a fat caterpillar. So they just look sort of like all over the place around a certain value. And here we can see our traces. So yeah, for each parameter, we can see more or less like what value they tend to like linger around in terms of distributions. What we are interested here mostly is elasticity magnitude or elasticity skew. They're essentially the same thing, just the signs are reversed. So each of these is a different skew, if I'm not mistaken, and we can see more or less like the values that they take. And then we can see the true value and the estimates. We can see they tend to be pretty close, but we can plot these. Once we have the distribution, the true values are these black lines, and the estimated intervals with 90% probability are colored, and then you can see the colors with the different categories here. We can see we're not far, but for some products, we are very far for some of them. But generally, we're doing fine. But since we know our data generating process, we know that something's missing here. So what's missing is basically the hierarchy between categories and also the regions and cross price elasticity. So that's what we're gonna look at next. So yeah, moving on to the second model. This is where we add hierarchies. Now this is interesting because that's where I think PyMC starts to get very interesting. The model keeps the same main equation, but it ties the elasticities together. So you have a category level and also a region shift, right? So yeah, adding these region and category terms essentially mean that snacks will behave in a certain way, essentials as well, but each product can deviate around that. So you should see tighter but more plausible estimates for some of the sparse products because of this partial pooling. And the same sign logic applies to the elasticity of the skew, but now elasticity is built on the log scale. So category means region shift and then this product offset. We exponentiate, so we stay in the sort of like positive magnitude space, and then we negate. That's why you see like hierarchy on log magnitude, because it keeps elasticities negative and lets, let's say, essentials versus beverages versus snacks sit as sort of like different baseline levels. So the partial pooling means the noisy skews, the noisy products, they sort of get pulled towards the category instead of just flying off. If we look at the DAG here, you can see there's like more structure upstream. You can see, for example, the category here and the region both affecting the elasticity of the skew, and then the elasticity of the skew affects the observed quantities. And in the recovery plot, we can see, our sort of like model diagnostics again. We can see that the same sort of like fat caterpillar pattern here on the right. And we can also take a look at what we are estimating in terms of elasticity versus what we had in our original data. So you can see, for example, if we're looking at categories, the true value for beverages was -1. We got -1. Here it was -0.45. We got -0.53. So yeah, we're always like reasonably close, but we can see that much better here. We can still see some of them are off by a significant margin. So we're gonna compare the three models at the end. It's hard to compare them just visually, but you'll see that model 2 gets slightly closer to truth than the model 1. And finally, we can move to model 3, which has both hierarchy and cross-price elasticity. Now that's basically the full story. The sort of own price block, it matches model 2, basically. So for every ordered pair in the same category region, cola reacting to juice's price and so on, we add a gamma. That's what we see here on the cross price. So that's what's been added on top of model 2, basically. We can see that the gammas, they get a hierarchical prior by category. So pairs in beverages, they share information without being forced identical. In cold, that's a sparse matrix of competitor log prices times those coefficients. So it's the same log quantity column with a sort of richer mean. For interpretation, the positive cross price means substitutes. So essentials in the simulation are almost not substitutable, but beverages and snacks have stronger cross effects. And then if we take a look at the DAG, now that starts getting a bit messy. But what's interesting is that you can see the cross pair here. So you have a sort of cross offset that impacts gamma pair as well as a cross for the category. So both the category and the pair will sort of like impact this gamma for each pair. And that's what's giving us, the impact of orange juice price on Coca-Cola, for instance. Same story with model diagnosis, so I'm not gonna spend too much time here. Yeah, and then we can see each of the true versus estimated values here, but also we can see them plotted here. So here we have the estimated cross price elasticity, so that's the average, and the true cross price elasticity. So ideally we want everything to be on this diagonal here. Essentials, they have almost no cross price elasticity, so they're close to zero. Each category has a sort of well-defined cluster here that revolves against around the diagonal. Now, when we compare models, essentially what we want to see is how well do we recover our true parameter. So here I'm just like consolidating the three first visuals. But what's interesting maybe here is to take a look, because what's really interesting for this exercise, we're interested in estimating the on-price elasticity. So here we calculated the mean absolute error for each coefficient. So not the model, like not the quantity, but just the coefficient. What's the mean absolute error on each model? We can see it significantly decreases, especially from model 2 to model 3. And we can also see the cross price mean absolute error for each category as well as the controls. But yeah, what we are mostly interested in is recovering the true parameters that we used in our simulation for both on price and cross price. And here we can see actual quantity versus predicted quantity, and take a look at the root mean squared error for each model, and how adding the cross elasticity was the thing that apparently had the biggest impact in our model. Yeah, so that's it. I think there are several ways that this can be improved. I'm particularly exploring now other types of models and not just log-log. There are some interesting results with the sigmoid functions that I want to explore further. But that's it. I'll be sharing the code. I hope this was useful. And yeah, of course, like one of the interesting next steps as well could be running some optimization. Okay, so what's the optimal price that will maximize revenue? And yeah, that's why I'm exploring other functions besides log-log. Yeah, let me know in the comments if this was useful, if there's something I missed here. I'm honestly studying PyMC and elasticity, so I'm open to any feedback that you might have. Thanks a lot. Take care. Bye bye.